could not have a better first speaker tonight. Dr. Jim Olson is not only the founder of Seattle-based Blaze Bioscience, but he is also the leader of a cancer research lab at the Fred Hutch Institute and the inventor of cutting-edge tumor paint technology that we're going to be spending a lot of time to talk about tonight. So, for those of you who don't know, TILE stands for Talks on Innovation, Leadership, and Entrepreneurship. And we could not have thought of a better person who exemplifies each and every one of these traits than Dr. Jim Olson.
So tonight we're going to be beginning with an interview led by Thomas and I, and then it'll turn into an audience-based interview with you guys. And if you won't mind silencing your phones, just so people can not get distracted during this event. Okay, so let's start with something basic. I know we have a lot of prospective doctors or biologists in the room. So how did you become interested in medicine?
Well, at first, actually, I knew that I was going to be a doctor when I was 4 years old. And I say that knowing that most people don't know that they want to be a doctor until college or even later. But in that case, we had a family medical dictionary at home. And it happened to have these really cool transparent pages that you looked at a human, and then when you flipped the page, that page had the skin on it, and you could see the nerves and the muscles. And I see all the people that are my age nodding their heads, you know. And then you flip the page again, you can see the bones, and it just went down through the body. And I just thought that was so fascinating to have insight into the human body. So it was really, I briefly had thoughts of doing other things, but from that time on, but I anticipated that I was going to be a family doctor and going back and working in rural Upper Michigan. And so my career trajectory went very different than that.
So from there, how did you get into oncology and pediatrics in specific?
Yeah, so as I mentioned, when I applied to medical school, I applied to be a family doctor. That was my intention. I went to the University of Michigan. And what I found when I was on my clinical rotations was that at the end of every day, no matter whether I was on surgery or OB-GYN or whatever it was, pediatrics, that I was sitting by the bedside of a cancer patient. And I just found myself drawn to them, whether they were anxious about the surgery the next day, whether they had chemotherapy and they weren't feeling well, and I was just kind of helping them get through the night. Whatever it was, I felt myself drawn to them. And I think that should probably maybe be a theme tonight is you know, when you hear or feel that you're being drawn towards something, whether it's a career or something that you want to do in terms of an experiment, when you feel that strong draw, it's important to realize it. I think it's also important to realize sometimes when your emotions don't match what you'd expect them to match. And there's two instances of that I think are pertinent to the question you asked. So one was, I applied to medical school, and I got into my first choice on the first day. And you would think that I would be elated about that, and that I would go out with my friends and be excited and all that. But I felt this utter disappointment instead. And I couldn't understand why I felt that disappointment. And did I choose the wrong school? Did I really not want to go into medicine? What was it? So my friends all went out and celebrated that night, and I stayed in. And I started looking through the medical school application books, trying to understand what was going on. And deep down, it took me a while to realize this, but deep down I realized that I had done a summer of research just to help me get into medical school, kind of something to help build the resume, get a little experience, get a little exposure. And I realized that by going to medical school that I was going to be leaving that behind. And I started thinking for the first time about doing both medicine and research. And I looked into these MD PhD programs, and ultimately I tore up the acceptance to the first choice of med school, and I started all over applying to MD PhD programs. And I got rejected from the first 4 that I interviewed at. And then somebody took pity on me and let me in. And so that turned out to be really right for me. And then the question about pediatrics really came by surprise. I was planning to go into adult medicine, and I knew I wanted to be in cancer. I was going to do radiation oncology. Again, I had applied for radiation oncology residency programs. And my last rotation of my third-year medical school was in pediatrics. I was taking care of this beautiful little 7-year-old girl who had neurologic problems. And we couldn't understand what was going on with her brain and her nervous system. She started losing more and more neurologic function every day. We could kind of see where it was heading. We could see that for reasons that we couldn't understand, this little girl was going to die from neurologic degradation, damage to her nerves. And so I spent a lot of time talking to her family, a lot of time talking to her. We could see that she wasn't going to be able to breathe soon, and we're going to have to potentially put her on a ventilator or make a tough decision not to put her on a ventilator. And her parents chose not to put her on a ventilator. There's no indication that this was going to turn around and get better, and they didn't want her to live a vegetative life. And so she passed away. And it was the first patient that I cared for who died, and it was a little girl. And so, again, you'd think, what should I be feeling that day, right? It should be profound sadness. And as I was walking home from the medical center, instead of feeling profoundly sad, I felt a little bit light, and I felt very positive, and I couldn't figure out why that was. So rather than just saying, oh, I wonder what's going on there, I actually went down and I sat by the river, and I thought about why do I feel better than I would think I would feel today. And what I realized was that a few hours after that girl died, I think a lot of parents of a child who had just passed away would just get in the car and get away and put the hospital behind them forever. But they spent 2 hours looking for me in the hospital. And when they found me, they gave me a really warm hug. And they said that because of what I had shared with them, her death was as beautiful as her birth or her baptism. And that they realized that a life that was 7 years long was every bit as good and beautiful as a life that was 70 years long. And it was my words that gave them comfort. And so I really thought about that, and I kind of realized that day that I had something to offer, even when medicine didn't go the way we wanted it to go. And so once again, I went home and I tore up my application to radiation oncology, and I started all over in pediatrics. And just as a little funny ending to that, nobody would have guessed that I was going to go into pediatrics. It was my first day on my pediatrics rotation. There was a little boy who needed a lab test, and I went down to the playroom to get him, and he really didn't want to go for his lab test. And so I was trying to make it fun for him, and I just said, how about if I give you a piggyback ride down to get your lab test? And he said, okay. So I hoisted him up on my shoulders, and as I did it, I smashed his head into the fluorescent light. And the fluorescent light came swinging down, and sparks were flying, and the bulb burst. And the chairman of pediatrics was walking down the hall, and he goes, what the hell are you doing? So it was an inauspicious start to my pediatric career that day.
And that start led you to, you said to have a goal where you said your goal in pediatrics was to walk into any room and give child hope. And I think one way you've done that is through Project Violet. Can you describe a little bit about Project Violet to us and talk about what its goal is and how it got started?
Sure. Project Violet it's really a philanthropic front door to the research that we do. Right now in my lab, I take care of kids with brain tumors in the hospital over at Seattle Children's. And my lab does research to discover new cures, new therapies for these kids with brain tumors. And a lot of times when ideas are new and you're just getting started, it's really hard to get funding from the National Cancer Institute or other organizations. And so we have a philanthropy program where people, our patient families, their friends, others can donate to the lab. And Project Violet is that. And it's named after a little girl named Violet who I cared for a number of years ago. And Violet had a kind of tumor that when I see the MRI scan, I know even before I meet the patient that patient is going to pass away from their tumor within a year. It's a uniformly fatal type of cancer. It happens only in kids between age 2 and 9. And there's no survivors that my colleagues or I've ever heard of. So when I meet a child, I know that that's their future. And we talk about it openly through the course of treatment. And with Violet, she knew that she was going to be dying in a few months. And she asked me, why don't you know more about my type of cancer? Why is it that researchers haven't figured out something about this cancer that could offer some type of cure? And I said, the problem is that your tumor is in your brainstem, which just connects your brain to the whole rest of your body. And if surgeons took any part of it out, they could leave you paralyzed. So we don't take these tumors out. And because we don't take them out, there's not tissue samples that we can study. There's nothing for us to study because there is no surgery. And so she said, well, when I die, I want you to take my tumor out and I want you to make tools and share it with researchers all over the world so that people can learn about what I have so other kids don't have to go through this. And I just thought that was so generous that I wanted our program to be named after her. And so we chose to do that. And so far in the last 4 or 5 years, we've raised about $13 million through Project Violet, and that has helped me build a 45 scientist research team. And basically we have a small biotech company within the Hutch that in an academic center we built a little biotech company, and we're doing some really exciting research because of that.
So transitioning to tumor paint, which is one of your maybe most well-known innovations, would you mind describing tumor paint for those of us in the audience who are unfamiliar?
Sure. So in 2004, I was taking care of a 16-year-old girl who had a brain tumor. And we saw on her scan that it was a high-grade brain tumor, it looked like a glioblastoma, which is one of the tough ones. And she went to surgery, and the surgeon who took her tumor out had been trained at Harvard, had worked for 25 years as a neurosurgeon, operated on her for 16 hours, and following Wednesday, when we did her MRI scan to see how the surgery went, what we saw was that there's a big piece of cancer left behind. And the reason there's a big piece of cancer left behind was because with all of his skills and knowledge and all the tools available, he thought that was normal brain. And he thought that if he took it out, he would leave her paralyzed or damaged in some horrible way. And so he left it behind. And he and I together that day made a commitment that we were going to find a way to make the cancer light up in the future so that other surgeons could actually have guidance that would help them see the cancer, distinguish it from the normal brain. We had no idea how we were going to do that, but over the next 6.5 weeks, one of his students and I met every night until we came up with an idea. And the idea, as crazy as it sounds, was to use this little mini protein called a peptide that comes from the Israeli death stalker scorpion. And all we knew about it at the time was that the thought was that it blocked chloride ion channels, so it was called chlorotoxin. And the kind of chloride ion channels that it was thought to block, I knew was not in the normal brain. So I thought maybe this is something that could actually distinguish the brain tumor from a normal brain. So we decided to add a little fluorescent tag on it, a little molecular flashlight. And we said we'll grow a human tumor on the back of a mouse, and then we'll inject this molecule called tumor paint into the tail vein of the mouse and see if the cancer lights up. And if it does, we'll do more experiments, and then I'll go back to the drawing board. And so we made the molecule, purified it, tested it, and then we injected it into a mouse that had a human brain tumor on its back. And about an hour later, the tumor on the back was bright fluorescent green, and the rest of the mouse was not. So here we have 2 grown men in white lab coats dancing and shouting. I can't say the words that we said here, but it was, yeah. And we were really excited, and that was in 2004, so that was 13 years ago. And now tumor paint has since been developed all the way into a drug for human patients. We've now treated over 90 patients in Australia and the United States, and we have a meeting with the FDA in November of this year to help design the last trial that would be needed for them to give us their first approval on the drug. So we're getting close.
Very exciting. And could you speak a little bit about, we talked about like the scorpion and thinking outside the box to come up with the solution here, but what is the thought process, or like how do you even get to that stage where you consider using the scorpion venom for the tumor paint?
Yeah, in that case, the neurosurgery resident who came to my lab wanted to do experiments that would help him understand what is different between the brain tumor and the normal brain. And then if we knew what was different between the two, we could actually try to get a molecule or design a molecule that would distinguish the two. My concern was that the experiment that he was proposing would take the whole year that he had to work in the lab. And so I said, let's try something different. There's lots of researchers that study brain tumors and lots of researchers that study brains. And so every day I want you to learn what's on brain tumors, see if it's also on the brain, and just scour the scientific literature, look at all the databases, come to me every day and say, these are the things I looked at today. these are the three that I thought had the most merit. Of these three, I prioritized this one for these reasons. These are the things that would make it work. These are the things that give me doubt that it might not work. And let's have that conversation every day. So every day at about 6:30 at night, we would sit down and have that conversation. And every day by the time we finished, I would shoot down all his ideas. And it wasn't because I was being negative or because I didn't think he had thought it through, but with my experience, I could see where the flaw in logic was or where we would run into a problem. It might be that what he proposed would distinguish brain cancer from the normal brain, but there's no way it would ever get across the blood-brain barrier, which is the protective layer that keeps things out of the brain. Things like that, you know. So you could, you know, that's what the gray hairs for. You get experience, you get knowledge, you get, you know, you see things that sound good and then don't work. And at the end of 6.5 weeks, he came and says, now we're scraping the bottom of the barrel, but there's this scorpion, there's this ion channel, you know, and I thought that actually had a lot. He didn't have a lot of enthusiasm for it, but I was really excited. I thought that could distinguish the brain from the brain tumor. If there was ever a critter that could get something across the blood-brain barrier, it would be a scorpion, right? They'd paralyze their prey. They have to act fast and inject something that gets all the nerves in the body. And so I said, let's try it. And so that was the thought process behind that. And that was the only molecule we ever worked on. We didn't screen hundreds of thousands of molecules. You know, a lot of stuff that we do in the lab fails. Over half of what we try in the lab fails. But that's one where the first thing we tried after thinking really carefully didn't fail. It's progressed.
And can you speak a little bit more to looking to nature for finding answers in medicine? Is this like a theme that's popular or common in all of medicine today, or is it more focused in cancer or oncology?
Yeah, that goes in waves. I think that scientists and physicians are very good at understanding what's out there, and they're always looking for tools so their minds are kind of cultivated to look for things. You know, jellyfish glow, and so people isolated that gene, and now we use it to make things glow in research mice, for example. A lot of early medicines came from nature. Vincristine, one of the drugs that I use in my cancer patients, came from the periwinkle plant, the vinca, that you guys see in your yard or people's yards, the little purple flowers. So people have isolated things from that. In my lab, when we developed tumor paint and then we spun it out into Blaze Bioscience, then some of my best scientists that were working on it went with the project into the company, and I had a chance to kind of reinvent my whole lab. And so I thought, what could we do that nobody else in the world can do? Because if you I trained for 18 years after high school. I get one life, and I'm not going to use it to do something that a lot of other people do. For me, that's really important, is to try to create and change the world through the work that I do. That's kind of a guiding, driving principle of mine. So what can we do that nobody else in the world could do? And I realized that we've been working with these little knotted proteins for a decade. We really learned a lot about it, and I had learned along the way that other plants and animals besides the scorpion make these little knotted proteins, and that they could potentially be really good drugs for humans. Well, like most good ideas, when I looked into it and read the papers, it turns out other people had that idea in 1990, a long time ago. And then I started asking why, if they had the idea back then, haven't they made good progress with it? What I realized is that these little proteins are very hard to make in yeast or bacteria, and that's what scientists and biotech companies and pharmaceutical companies use to make their protein drugs. And so I actually recruited a scientist from Amgen and a scientist from Fred Hutch, and we created a way to trick human kidney cells into making these mini proteins from plants and animals and a lot of other organisms. And we discovered, all the other scientists in the world had discovered about 2,000 of these molecules over 40 years. Our team discovered 80,000 more of them, and we did that in a day and a half. And the reason we did it differently than the rest of them is because the way the others were discovered is people would catch a scorpion, they would tape it to their research bench, they would touch its tail with a little electrode, and a little drop of venom would come out of it. They would capture that venom in a little tube. They would put it in a machine called a mass spectrometer, and that would measure and see what was in there. And I'm not going to do that. Are you kidding me? I'm not touching a scorpion. And so what we did instead was we said, you know, this is 2017. It's not 40 years ago. We live in Seattle. So instead I hired a programmer that I recruited from one of the Bay Area startups, and he wrote a Python program, and it just went through all the genomic databases in a day and a half, and we had established what the rules were for these molecules, and it found all these molecules in every plant and animal that makes them and that has had their genome sequenced. And so that then became our new denominator, our blueprints from which we could make. We now have 10 million candidates that we've made variations of those.
So one of the most impressive things I've heard regarding tumor pain is that it's much more sensitive than MRI scans. So how do you achieve this level of precision? How much more sensitive is it?
Yeah, so in a number of ways, tumor pain is different from MRIs. An MRI is something that you would do with a patient lying on a table, maybe the week before surgery or the day before surgery, and then you have that static image of that point in time on the computer while you're operating. Well, the problem is the brain is filled with sacs of fluid, and it's surrounded by sacs of fluid that keep it from getting damaged when we have head injuries. And because of that, when you cut into the brain and start doing surgery, all the anatomy shifts and changes right away from the first 5 minutes of surgery. Everything that's on the MRI is outdated now because the tumor just moved 1.5 centimeters because some of the fluid drained or something like that. With tumor pain, you inject it in the vein of the patient the night before surgery or the morning of surgery, goes through the whole body, it binds to the cancer cells, and it gets flipped inside the cancer cells. So when you shine a laser on it, you're actually looking at the cancer. And so if you pull the brain aside with a little surgical instrument, the tumor paint goes with it. And if you cut some out, the tumor paint is in it, and you can look at it, and the pathologist can see that there's tumor paint in there. So that's the first and most important thing, is it's real-time imaging. You can see it while you're operating. The second thing is that we learned about sensitivity by experiments. Sometimes we can't predict things, and we certainly weren't building it to be that specific. But we were looking at a mouse that had prostate cancer, and all the lymph nodes that were filled with cancer cells were lighting up. But there's one little area that lit up, and it didn't feel like a lymph node to me. It just felt like a little fatty wad of tissue. And so I took it out and I sent it down to pathology, and I said, I don't think this is a lymph node, but it lit up. What's going on here? And they called me back and they said, it's not a lymph node, it is a little bit of fatty tissue, but running through the middle of the fatty tissue is a lymph channel. It's a drainage channel. And inside that lymph channel is about 200 cancer cells that were traveling from one lymph node to the other. So that was really the day that we learned how sensitive it was. You could never measure 200 cancer cells by MRI. You need probably 1 billion.
So then why use an MRI instead of tumor pain?
Well, MRIs are great because you can do it without cutting into the patient.
Yeah.
So you can use it for monitoring if somebody has bad headaches or drooling out of the side of their mouth or other symptoms that could be a brain tumor. You get an MRI and see, is there a mass there or not? When we look at the MRI, it tells us what's the location of it. That gives us an idea of what kind of tumor it would be and whether we need to cut it all out the first time we go in or whether we just need a little biopsy of it.
Yeah.
We use MRIs to monitor after treatment every 3 months to see if the tumor's coming back, and we could use tumor paint for that. So these are complementary.
Yeah. Are there any risks that are involved with tumor pain? And to what degree is surgery made easier by it?
So far we've treated about 90 patients, and when we grade side effects in clinical trials, we have a scale of 1 to 4. A scale of 1, a grade 1 toxicity, would be like a queasy stomach or a mild headache or a little rash, something like that. That's a grade 1 toxicity. Grade 4 toxicity is like, I can't breathe and I need to be intubated, or my immune system has been so suppressed I can't fight off an infection and I might die. With tumor paint, we haven't had anything more than grade 1 toxicity in all 90 patients, and most patients haven't even had a grade 1 toxicity. So far it looks to be very safe. The FDA requires that we look at hundreds of patients because the way statistics work, you can have 90 patients with no side effects, and then you can have something horrible because it happens rarely, and one of those rare patients wasn't in your first group. So we do have to treat a lot more patients before we get full FDA approval.
Yeah.
So another big problem in cancer research, from what I understand, is not knowing whether a patient is resistant to a drug yet. And I understand you have a pretty unique solution for testing whether a patient has already been resistant to a drug they've been treated with. Can you talk a little bit about that?
Sure. So, yeah, it's really one of the ways that I come up with experimental ideas is I go to clinic each week. And when I'm in clinic, before I actually start seeing patients, I just sit down quietly when the room is kind of still, and I just say, what am I going to do today that I don't want to be doing in 20 years? Some interaction or something that I do today is going to strike me as, I hope we can get past this. I hope we look back and say, God, I can't believe we used to do it that way. And so one day, I was taking care of a little boy from Alaska who had recurrent cancer, and I was about to write a prescription for him for chemotherapy, and I realized that I have absolutely no idea if his cancer is already resistant to the drug that I'm going to prescribe. And if it is, that means that the drug that I prescribed is going to cause him toxicity, because all chemotherapies cause toxicity, and it won't provide him any benefit. And beyond that, he will be stuck here in Seattle at our hospital instead of back in Alaska with his friends and his family. So there's a lot riding on this, and it's completely a black box. So people in the 1970s and 1980s spent probably a couple $1 billion, and there were a lot of really smart people that tried to ask questions like, if you take out cancer cells from the patient's body and you put them into little test tubes or dishes in the laboratory and incubate them with different chemotherapies, can you predict which chemotherapies they're sensitive to and which ones they're resistant to? And after all that work, it turned out to be a bust. You couldn't predict at all. The reason for that is because cancer cells growing in the plastic dish behave entirely different than cancer cells in your body, where they're interacting with the normal tissue, where you have your immune system. There's so many reasons. And so we came up with a device that you inject through the skin and into a patient's tumor, and it has about 8 or 9 needles on it. You inject those needles deep into the patient's tumor, and as they retract and come out of the body, they leave behind columns of different chemotherapies or drug combinations. We then let the patient walk around for like 3 days, and those chemotherapy drugs are working on the cells in the cancer right nearby those needle tracks. We put in fluorescent dye so we know where each needle track is. The surgeon then removes the tumor from the patient's body. We fix it and we cut it crosswise to all those needles, so you can actually see in what we call an internally controlled experiment how drug A behaved, how drug B behaved, how drug C behaved, how the combination of A plus B behaved. You can see whether the cancer cells died or not. And if it's a drug that we're thinking of giving the patient and they were bathed, like those cancer cells were bathed in lots of that drug and they didn't die, I'm not going to prescribe it for that patient. So we're now in human clinical trials with that device. It's being used at Seattle Cancer Care Alliance. We've done it in patients with lymphoma and non-sarcoma. And we're also looking to use it in a slightly different way, in which companies that are developing new drugs that help the immune system recognize cancer have no way to test those in advance, because you can't test them in mice because the targets in mice are completely different than the targets in humans. So this would be a way that you could actually take engineering doses of those or batches of those and prioritize. I should take this one forward into clinical trials and I should leave that one behind. So we're starting to work with drug companies to help them prioritize the drug candidates.
So if we take a step outside of cancer research, you've done a lot of work in Seattle. So in your opinion, how do you think Seattle is fostering an environment of innovation, especially in the field of STEM?
Oh, that's a great question. We're very fortunate that we have Boeing, Microsoft, Amazon, all these companies here, because not only does it create an opportunity for those people who do well in STEM and go into those fields, but it also creates a pressure. So, when those companies see that the university is not putting out enough good students that have graduated that can fill those job ranks, they kind of put pressure on the university, and with pressure often comes resources. And I think that's happened at the college level, at the high school level, going all the way down many levels. So, and I also think that people that are